Okay. Is everyone here? Okay. Right, so our last speaker today is Armin from Vienna, and he'll tell us about quantum heat engines, which you already heard a little bit about in Ralph's talk, and both Nato and Ladina also built some kind of heat engines, and now we'll get into the details of this. So.
Okay. So welcome everyone to this two-part talk on the topic of quantum information in quantum thermal machines. This talk was originally supposed to be given by Geraldine Hack, who unfortunately couldn't be here. So instead you are left with me. In the first part of the talk, I'm going to not talk so much about quantum information, and instead focus on quantum thermal machines. We'll do it from the ground up. We will see what a quantum thermal machine can do, how we should think about it, how we can model it, how it relates to classical systems, and how we can talk about its efficiency. This we will do through a concrete approach based on two seminal examples of quantum thermal machines. And then focused on refrigeration, but we will see that with small tweaks, you can turn these machines into heat engines and heat pumps if you so wish. In the second part of the lecture, we will look a bit at quantum information concepts, centered about the question of what warrants us to view quantum thermal machines as truly quantum processes. What can these quantum thermal machines do that classical systems truly cannot? And for this, we will introduce some basic notions of quantum information theory and then try to apply it to our concrete machines. So let's get started. I think it's instructive to recall the basic working principle, the basic modus operandi of a classical thermal machines that, of course, we're all familiar with and rose to fame with the whole Industrial Revolution. So recall quickly that an engine is a process that exploits a flow of heat from a hot system to a cold system through a cold bath through a system, and in the process extracts some work. If you want to run an engine in reverse, you obtain a fridge. A fridge will then reverse the heat flow. So now it will go from the cold system into the working environment and then into the hot bath. And of course, this cannot happen spontaneously because of the second law. So to make it happen, we need to now input some work in the process. So the modus operandi of a classical thermal machine is simply harness a heat current between a temperature gradient to do something that you're interested in doing. And we will see now that the quantum counterparts of these machines operate by precisely the same principle. We will use a heat current to do whatever task we're interested in, but the main difference will be that the system on which it is based will no longer be classical, it will be a quantum system instead. So the seminal example of a quantum thermal machine is the one that was introduced already in 1959 by the work of Scoville and Schultz. Well, this original observation was made already in 59, but the proper details were fleshed out only in 1967. It's based on interpreting what is then known as the three-level maser as a quantum thermal machine. And for the sake of concreteness, we will focus on viewing it as a refrigerator, but you might as well view it as an engine with small changes. I might add that a maser is basically a laser that operates on a wavelength that you cannot see outside the visible spectrum. So now the system that through which the heat currents will flow will be a three-level quantum system. So we can draw it here. So it's a system like that. It has three possible transitions. You could go from the ground, the first state, up to the second one. Let's call this energy gap EC. The indices will become obvious in a moment. Then if you transition from the second level to the third level, then we can call that energy gap EH. And if you take the big transition from the top to the bottom, then we call that energy ER. And okay, to make sure that the energies add up, we need to insist that the ER is equal to EC plus EH. Now, the reason we use these indices C, H, and R is because each of these transitions are going to be connected to a respective thermal bath, which is going to be cold, hot, and at room temperature. Of course, the room temperature here doesn't really mean room temperature. It just means that the room temperature is hotter than the cold one and colder than the hot one. But the main assumption that you will go into this perhaps somewhat artificial construction is that although the system itself is one physical body, the transitions only see one bath each. So somehow you isolate the other transitions from the baths that you don't want them to interact with. So the cold transition here will be interacting with the cold bath at temperature Tc. The hot one will be interacting with a hot bath at temperature Th, and the room with a third bath at temperature Tr. The working principle here will be the same as in a fridge. That is, you will hope that the cold bath will spit out one quanta of energy into the system, cause an excitation, then have the hot bath that typically here works at the working medium to spit in one quanta of heat here to make one more excitation, and that then you will then drop down to the ground state and spit that energy out into the room, thereby effectively cooling the temperature associated to the cold transition. That's what we are aiming for. But of course, you would have to tune all your parameters to make sure this happens. And we will see how to do it. Now, it's instructive to momentarily forget about the cold bath and take a look at the ratios of the populations. We will see that if you forget about the cold bath, then the population that sits in the third level, the top one, its ratio to the population in the ground will be determined by the energy gap associated to this and the temperature. So this will simply be e to the minus E room over the temperature associated to it. By the same token, the ratio of the populations between the third level and the second level will be given by this energy gap and the temperature associated to that. So we will now have that Q3 over Q2 will be e to the minus E hot over the hot temperature. Of course, you put these two relations together, you can also derive the ratio of population between the first excited state and the ground. So you just need to divide this one by this one to get Q2 over Q1. And let's see that we get this one right. You will get e to the, what is it now? And you will get EH over TH minus ER over TR. This does not look equally instructive, but there is a simple trick to make it look more informative. And in fact, Ralph in his talk on Tuesday briefly touched on the concept of a virtual qubit. And here it's very helpful to invoke virtual qubits and even more virtual temperatures to learn something from this relation. What this means is that we want to think of this relation just like one of these relations. That is, we want to write it as if it was the energy associated to the cold transition divided by some temperature. But this temperature, of course, will depend on the circumstances, the energies and the other temperature of those baths. So we need to introduce this virtual temperature, which acts as if this transition was in an environment at this temperature, although no bath at temperature T virtual really exists. So this is, in a sense, a mathematical trick. And to make an equality here, we need to define our virtual temperature in terms of the hot and room energies and the hot and room temperatures. So to make sense of it, we need EC in the numerator, and then, maybe it's getting too small, C room over T room minus E hot over T hot. So yes.
Sorry, I don't understand why can't we just do Q2 divided by, so population of 2 divided by population over 1, exactly in the same principle as we did for Q3 divided by Q1. So why isn't it e to the minus e to the minus EC divided by TC?
Because it starts with disconnecting the cold bath.
Ah, sorry.
So, and then imagine that you have this steady state already, and then you switch on the bath, and then energy will start flowing in the system because you put it out of equilibrium. And then you will get this effective virtual temperature. And you want to see if this one can be used to cool your system. So, okay, so this is our virtual temperature, the thing that the system effectively sees in this transition, although it doesn't really exist. So, but this is an awfully useful concept because it can be used to tell you very quickly whether you will see cooling or not. Indeed, the cooling condition for this system would just be that the temperature of the cold system is hotter than the virtual temperature. Because then by the second law, heat will flow from the cold one into this effective virtual bath that doesn't really exist, and thus you will achieve cooling. So this is what you need in order to make your machine work as a refrigerator. If you want to make it work as a heat engine or as a heat pump, you just need to identify very similar conditions under which your virtual temperature now acts the other way that you want. So now, if you reverse this relation, you will have a heat pump. And if you want to create an engine, you need to achieve population inversion. That is, you put more population in the excited states than you have in the lower ones. So it's all about tuning these parameters in the right way to make your machine operate as you wish. So how well does this machine perform the cooling? How effective is it? Is it better if Lydia, is better if I stay here and put this up? So to talk about the efficiency of cooling, you need to introduce a measure of what this means. And the most popular way of doing it is through the so-called coefficient of performance that you may recognize from ordinary Carnot problems. So this coefficient of performance, that's often abbreviated as the COP. It's defined very intuitively as the ratio between the heat that you extract from the cold bath, which is what you want to do for cooling, to the ratio of the heat that you have to take from the hot one, that is your work cost. So the better this ratio, the more efficient is your cooling. So this is the heat current out of the cold bath divided by the heat current out of the hot bath. Now, somewhat hand-wavily, which will be justified later in this lecture, you can have some intuition that these heat currents ought to depend up to some factor that you don't really care about, which should depend on the energy, the temperatures. This should be proportional to the energy of the corresponding transition. So these proportionality factors will vanish, and this will essentially be the equivalent of the cold energy over the hot one. A proper justification for this will be apparent in 15 minutes or so. So how can we calculate this coefficient of performance? I should add that this is often called the efficiency, but you should note that this is not really an efficiency because this number can be bigger than 1. So it's not so instructive to think of it in that way, but sloppy language is often here to stay. So let's take a look. What will this be? To evaluate it, we have to look at our cooling condition. That is that the cold bath was hotter than the virtual temperature. Now, from the virtual temperature, which we have down here, we can immediately get rid of the room energy. We can express it in terms of the cold one and the hot one because the energies had to add up. So if you do that, you end up with an expression that depends on the cold and the hot energies and the room and hot temperatures and the cold temperature that you have from here. So you can sit down and rearrange it rather straightforwardly, and you will find that this condition is perfectly equivalent to the COP, which is now defined through EC over EH, being smaller. Okay, let's see if I remember this one right. The cold one minus the hot one minus the room divided by the hot one minus the room and the cold. So this is perfectly equivalent. Yes.
I'm allowed to ask a question, but I'm just slightly confused about something that I couldn't resolve for myself, because at the very beginning you had these sketches, what is a fridge, and it takes from energy from the cold to the hot. But now what is you now called the hot bath is also actually something that delivers energy. So shouldn't the room temperature thing hot one of your sketch?
Yeah, so I am guilty of abusing notations here. So indeed, what the hot one is in this picture is the work bath, and not the opposite. No, this is the room temperature. And this is confusing notations. So I should make it clear. The very hot system is the one that is doing the work. All right. And these baths are just there to create the temperature gradient. So yes, Renato is right. All right, so this tells you a bound on how efficiently you can do your food. This becomes even more recognizable if you take the hot bath, the one that is doing the work, in the limit of it being extremely hot. So let's take the hot temperature to go to infinity, just for the sake of argument. What happens? You can take a division up and down by the hot temperature, so then you lose this factor. Here you get a 1, and here you get a ratio. And then you take it to infinity, this one will vanish, and you're left with Tc divided by Tr minus Tc. And this you may recognize as the result you get from the Carnot efficiency for a refrigerator. And it tells us that in the best case, or just as we should expect, the efficiency of our quantum fridge is still obeying the good old Carnot limit. This result you can of course derive from the first and second law immediately. So anything that would violate this would indicate that we are doing something wrong. But it tells us that in the limit of the cold temperature being close to the virtual temperature, you can saturate this Carnot limit. But of course, when you approach this point, you do gain efficiency, but you do lose cooling power. But because the smaller the temperature gradient, of course, the heat flow will reduce as well. So these are complementary quantities. Okay, so with that said, let's go beyond the sort of earliest and simplest example of a quantum thermal machine and jump into something a bit more up to date. The main drawback, well, there are several, but the main one, in my opinion, of the three-level masonry interpreted as a refrigerator is the idea that you need to isolate your transitions from your buffs. So there is a single physical system, it's connected to a buff, but somehow the other transitions are isolated from influence from this buff. So if you want to make a more realistic and perhaps a more insightful quantum absorption refrigerator, you need to make it slightly more sophisticated. But much of the intuition you have here for the three-level system can be exported into the more modern construction. And this is a fridge now that dates to 2010 and was put forward by a work of Linden and colleagues. It's often referred to as the 3-qubit refrigerator. And the reason that you have to have the 3 qubits is twofold. Firstly, you want your 3 transitions that you had in the maser to now be put into separate physical bodies. So you can realistically connect them to separate buffs. 3 transitions, 3 qubits. The second reason that you want the 3 qubits is, of course, that you still need your third buff to act as the thing that propels your fridge to success. So your system will look something like this. You'll have 1 qubit, and then a second one, and then a third one. Now we need to choose the energies. And with complete analogy with what we saw here, we should choose a cold one here, a hot one here, and the room temperature one here. And before, of course, we needed to insist, just because energies need to add up, that the room was equal to the cold plus hot. This time, that does not necessarily have to be true, because we have 3 separate qubits. Instead, we insist on this as a construction, as a design premise. We need these energies to add up. And the reason will be clear in just a moment. So if this one drops down, and so does this one, the energy corresponds to jumping up on the room temperature one. And you can, of course, reverse these transitions as well. Now we want our 3 qubits to interact with each other. And to do that, we need an interaction Hamiltonian. So let's draw something like that. And we have to choose how we want to construct this. But before doing that, recall that there is also a free Hamiltonian of this system, which is rather straightforward. It's simply the sum of the Hamiltonians associated to each of the qubits. So you can have an excitation in the cold system, and then have nothing on the room and nothing on the hot. Or you can have nothing in the cold, and then an excitation in the room, and no action on the hot. And finally, the last case, where you have an action on the hot system. Like this. Now, this Hamiltonian, by construction, because we insist on this, has at least two degenerate eigenstates, which are, of course, those that correspond to these transitions. Those are when you have the cold system in 0, the room temperature one excited, and the hot system in the ground, and the opposite. This transition preserves the energy. But we have to be careful because there could be an accidental second degeneracy, which would be if the cold energy here equaled the hot one. Then you could have a flip-flop interaction between these two while conserving energy. So as a design condition, we're going to insist that the hot one is not equal to the cold one as well. So now we have just one degenerate subspace. We're going to insist, like so many other quantum thermal machines, to work in the regime in which the interaction Hamiltonian is weak. Weak meaning in comparison to the energies of the system. Its eigenvalues, these largest eigenvalues, should be much smaller than the energies you see in any of these qubits. And when you're in this weak interaction regime, the magnitude of the transitions will correspond or be suppressed according to the energy differences. So the resonant one will dominate, and that is why we have put this transition on resonance. So for simplicity, we consider an interaction Hamiltonian that precisely corresponds to this resonant transition. It has some strength G, and then it flips our qubits according to those resonances. Recall now, for recoupling, we do need to insist that G is a lot smaller than all of these energies, whichever one we pick. Furthermore, we need our three buffs. So the cold one now, the cold system connected to a cold buff, the hot one to a hot buff, and the room to the room temperature buff. So this is our fridge. And just like before, we now need to tune our parameters such that this thing achieves cooling. Cooling here meaning that the cold system is going to get colder. So we need heat, just like before, to flow out into the system and as well from the hot bath, which acts as the work source, and then we spat out into the room temperature one. How can we know how we should do that? To that end, we need to know how the dynamics of the system evolves. And that, of course, depends on the model you employ. For the sake of showing you more than one model, I'm going to begin with highlighting one that you have already seen to some extent, first in the talk of Matteo, rather briefly, and then to some extent in the talk of Ralph, which is the reset model. I find it instructive because it allows you to have a very simple intuition or a heuristic for how to model these systems. And as it turns out, you can also put it on a rigorous footing because it turns out to be a special case of an ordinary Lindblad master equation up to some ifs and buts. So it's a useful, handy thing for simple understanding of systems. Later.
Can you just stay on that side? The camera keeps switching left and right because you're in the middle.
All right. Okay. Okay, so the reset model. So the reason behind the reset model is simple. A change in the state, which is now the state of the three qubits combined, is first given by the ordinary von Neumann evolution. So you add up your free Hamiltonian and your interaction Hamiltonian and commute it with the state. This is, of course, just the closed evolution. And then you have your visit vectors. And here is where you get the very simple intuition. You imagine that the hot system is connected to the hot bath at some rate, gamma h. Similarly, you have some rate of connecting here, gamma c, and a gamma r here. So with probability or rate gamma k, the KF system interacts with the bath. Once that happens, you lose your qubit to the buff. So you trace out system K from your actual state. And the buff supplies you then with the thermal state of the temperature that it holds. And this system we call tau K. Right, so this one is specified by the energy ratio EK over TK. And now this is the change in your state, so you should remove the state that you had a priori. And because we are doing weak coupling in the Hamiltonian and the interactions with the buff, we are free to adopt a local master equation in which we can treat the buff separately, meaning that the qubit locally, say here, only sees this buff. You could object to this and say, well, can't this one see that one, for example, by the interaction Hamiltonian? And this could happen, but we try to avoid this by going to the decoupling regime. So this is one of the many approximations that go into the derivation of these master equations. So we will simply sum up these three contributions over the whole half and the room. So now we want to solve this. Typically, we are interested in seeing the behavior in the steady state regime, where all the dynamics are dying out. So the steady state of this equation is, of course, the solution to this one. Maybe I should take this one up here to make my point. If you insist on the steady state solution to this equation, it simplifies a lot. Differential is gone, and you're left with what is actually just an inhomogeneous linear matrix equation. The variable is, of course, your state, and it depends on a whole bunch of parameters. The three temperatures, the strength of the interaction Hamiltonian, the three couplings, your three energies, and so on. But in the end, it's just an inhomogeneous linear matrix equation. So you can solve it. I'm not going to solve it because it's large and cumbersome and doesn't teach anyone much. But instead, it's instructive to know that you can solve this one if you would like to bother. So equation like this, you can always write as some matrix acting on your variable plus some column matrix like this. So this is some square matrix, and this is some column matrix. So equations like this are, of course, straightforward. You just find your variable by taking the inverse of your square matrix and apply it to your column. Here, X is what corresponds to our state. You just take all the variables from your density matrix and put them in a list and call it X. So you can solve this. The full solution is cumbersome, so I'm not going to put it down. Instead, it's going to be in the notes I can add. So on Discord, I have already uploaded them. There you have the full expression for the steady state solution. But here, instead, I want to highlight some of its key properties to see what you can qualitatively learn from it and match it by your intuition. So the steady state, to start with, I put an infinity here, is going to be rather constrained. You could imagine that this state could be complicated, but in fact, it's not so much. And the reason is that in this system, coherence can only come from one single place. Interactions with thermal buffs never gives you coherence. The only place it can come from is through the interaction Hamiltonian. But recall that the interaction Hamiltonian is just connecting our two resonant transitions. So every single coherence in our steady state must be zero unless it sits in this little subspace. So our 8 by 8 matrix representing our three qubits will have some diagonal and some single off diagonal term, and everything else will have to be zeros. Now, the form of this thing can be put down on a nice qualitative form without going into all the details. It turns out that this thing is equal to the thermal state associated to the cold bath, tensor the thermal state associated to the room, and the thermal state associated to the hot. This is, of course, what you would get if you turn off the interaction Hamiltonian. You locally thermalize. Well, we don't do that, so we have another contribution, which looks qualitatively like this. These alpha and sigma, they depend on all the physical parameters that we're trying to avoid spelling out. So here, this is some dimensionless quantity. And this is a trace zero matrix. From this, we can take a look at the steady state of that qubit that we're trying to cool. So for doing that, we can trace out the other two systems and just keep the cold one. if you block the room and the hot system, this one goes, and you just compute a partial trace over this one. This is a straightforward operation. So you're left with the cold system. Maybe it's nice actually if I put the general one. Let's just put the K here. So you have the thermal state from the cave bath. And in addition to that, you pick up something that looks rather like this. Which means that this trace zero matrix reduces to some matrix that looks like the Pauli Z operator, up to some proportionality constant that we will not need to care about here. So this is more of a qualitative assessment of what the solution will look like. This one can tell us quite a bit. Look at the cold system. This density matrix here is diagonal because the tau is diagonal and so is the Pauli Z operator. Every single qubit state can be interpreted as a thermal state at some suitable energy to temperature ratio. So this is a thermal state if we decided to view it that way. And to make it colder, we need to make it a smaller temperature than the one that we started out from. So we need to increase the ground state population. So we arrive at the analogy of the cooling condition that we saw already for the maser. And the cooling condition will then be that this alpha thing is larger than 0. So whenever this happens, this machine acts effectively as a refrigerator. Lydia, how am I doing on time?
You could. You have 15 minutes.
Oh, nice. Okay.
So there was a question, I don't know what's the reason for subtracting rho, but I don't know where.
Probably in the master equation, I guess. Here, perhaps.
Yeah. Yes.
Yes, so the reason that you want to subtract rho is that you're looking at the change in the state at a very small time step. So here is the dissipative evolution, and you imagine in this heuristic that whenever the state changes, you lose a system to the bath, replace it with a thermal one from that bath, that's the new state, and since you're looking at the change, you remove the old system. So this is a crude one that turns out to be rigorous, but that's how to think about it, right? Okay, so much for the cooling condition. Let's see what we can say about the efficiency of this machine. And recall previously that we sort of hand-wavily claimed that the coefficient of performance, which is the ratio of the heat currents that you're interested in, will just equate to the ratio of the energies. From the reset model, we can see how this thing emerges. So in order to do that, let's take a look at the small variation in the state. So we do a small variation, which means that we evaluate the state at time t plus the small time step. And then we remove the state we held just before. And for the sake of, right, we should put the escape subsystem because that's the only one we're interested in. So let's do that. Now, if you do this, of course, here you will get the state at time t, and then you get your small time step times the rate at which you're interacting with the bath. And when it happens, you have your tau k that the bath supplies you, and the rho k, which was what you had just before. Again, this is just a change in the state at a very small step immediately from the reset model. And of course, we should also remove this one and not forget about it. So this one here will cancel that one, and you're left with a very simple expression that in the limit of a small time step, the change in the local system rho k in time t will just be the rate of interaction times the state that the bath supplies minus the state that you had just before. So this we can use to evaluate the heat current in this system. The heat current, which we can denote Jk, is just the expectation value of the Hamiltonian on the system K applied to the change in the state. Recall that this Hamiltonian is the sum of the free and the interaction one, but we're just looking at its interaction in the one of the number K. So when you have this, you simplify considerably. The interaction one, if you drop two systems from this one, you will have nothing left because it only induces coherences. So the partial trace taken of the interaction Hamiltonian is just 0, and you can forget about it. The free Hamiltonian was just the sum of the three separate free Hamiltonians. So if you ignore two of them, you're just left with the free Hamiltonian for the single qubit you're interested in. For that reason, this thing will simplify to the energy associated to an excitation in the cave system. And then you will have, you take the excited state, because that's what you get from the free Hamiltonian. And then you have this derivative. Maybe, is this getting too small, maybe? Okay, I'm being squeezed into the corner. If I erase a bit on this board. Yeah. So, any of you, if I erase something you were trying to take notes of right now, I repeat that all of this is in the notes that I put on the Discord. So you can find it there. Okay, so we were trying to compute the heat current. Okay, so the heat current was the energy associated to an excitation in the cave qubit, and you're looking at the excited state, so you should take the sandwich 1, and then you have the change in the state, which comes from the definition of the heat current. But this derivative we just calculated from the reset model. It sits there, so we can just put that in, and we get EK, and then 1, and then gamma K, tau K minus the local subsystem. So furthermore, the expression for the local subsystem is what we derived from our master equation. And where is that from? Here, in the steady state region. So we can take that and insert it into our expression for the heat current. So we see that you get the tau from here, which will cancel the tau from there, and then you are left with this factor. So if you insert that, okay, let's take out the gamma as well. Gamma K. Then you have, what is it now? Alpha over gamma K. Okay, it has a sign, plus minus, but this just indicates if you're flowing into or out of the bath. So this we don't need to care too much about for the purpose of the point here. And then we have this operator that we didn't bother to characterize properly, but it's just proportional to the Pauli Z matrix. So the gammas are going away, which is the good news. And now we are left with this expectation value. Of course, this is still depending on all those energies and all temperatures and the interaction Hamiltonians and your bath system interactions, but it does not depend on your choice of subsystem. The only place where that is entering is in the energy. So if we want to look at our coefficient of performance, which recall was the heat that flows out of the cold system at the cost of the one you have to pay from the hot one, which acts just like the work source did in the 3-level maser, then this will be that hand-wavy coefficient that we said will arrive if you try to compute this ratio. So these will cancel from here, and you will just be left with the energy difference between the cold and the hot system. And that is the justification for where these relations come from. Yeah, how am I doing?
5 minutes.
Yeah, actually, I prefer to stop. I think yes.
This may sound a little bit silly, but why are you interested in the steady state?
So the reason we're interested in the steady state is because if you choose to look at how the cooling performs over a long time, you will eventually arrive at the steady state. That's one reason. The other reason is that if you just want to look at a specific time instance, then you need to clock your system, and it will only be valid for that single moment in time. So you want this thing to cool eventually to the thing you want. Of course, it's reasonable then to wonder, well, how long do I have to wait until I come to that steady state? And here we have conveniently just forgotten about it. But that is something one should think about.
Okay. When it arrived, the reduced state of one subsystem broke infinity exactly. And there is leftover part proportional to sigma z. Why can you pull out gamma k and now sigma z is independent of the subsystem?
So this is where I'm sort of cheating a bit by not doing the proper calculation. So here I was just trying to highlight the main form of this calculation, because I didn't want to cover all 4 boards in it. So this operator, So the original operator that you got, that this one in the full solution. This thing depends on everything.
Yeah.
And when you take its partial trace, it again gets you some complicated expression, but you can qualitatively represent it the way I try to do here. And it turns out simply by root calculation that it drops out this system and the rest is independent of your choice of subsystem. So this is a simplification of a lengthy calculation that turns out to be this way. The full one is in the notes if you would like to see exactly how you arrive to it.
Okay.
We're asking why the tau k contribution vanishes.
Not sure I understand what you mean. The contribution to what?
It was a question.
Is asking about tau k. You said they cancel out.
Okay. Yeah, maybe that's it. Okay. So what I was saying is that when you compute the heat current here, you ended up in this expression. But you knew the expression for the subsystem, which is infinity here, the subsystem of your steady state. This one we calculated, and it was this one. So if you put it in there, this tau k will cancel that tau k, and you're good. That's how it went away.
And since the system is quantum mechanical, can it really reach a steady state? Because there's like this quantum recurrence, Poincaré theorem.
It will of course never really reach the steady state, but your dynamics know they will eventually die out. Because the steady state is an idealization, knowing it's in a time that never really happens. So if you want to make this properly rigorous, you should maybe talk about, well, how much will this fluctuation, how can I bound this fluctuation, and put some epsilons around it. But here, we're just doing the idealized limit. But you have to do that if you want to do it for real. Thanks. Any more questions? Okay.
And we'll be back at 12:30. Thank you. If everyone is kind of back, we will slowly restart. And just one more thing about Armin is that he signed up for the summer school as a participant. And he's a postdoc, and we have very limited places here. We're really at the room capacity, and we couldn't fit more people. So we have very few postdocs here, and we thought we only let in the postdocs that we feel at the moment a bit disconnected from the quantum thermodynamics community and could learn the most. And his motivation paragraph said, well, I know nothing about quantum thermodynamics, and I have these 3 papers in the topic, and they're like, clearly he knows too much. We'd love to have him, but we can't, we need to prioritize other people, the students. So then it was very lucky that, we're sad not to have Gerald in here, but then we managed to have it. Anyway.
It's good that your filter systems work.
Just one more minute. Remember that we have the exercise class after this, after the coffee break, so we'll be outside as usual and on Discord. So you can continue, yeah?
Okay, so welcome back to the second part. Before getting into it, I got a couple of good points made to me by Ladina and yes, sorry, what was your name? Somewhere. And that was that, okay, why isn't this derivative vanishing here? Wasn't this a steady state which is defined by the derivative vanishing? And the answer to that is that here we were looking at the heat current, which is defined in terms of the dissipative part of the state. We're only looking at the dissipation, otherwise this would be 0 by definition. So that is an important point. The rest of the change in the state, which should cancel out the dissipative part, would come from the closed evolution. So I sloppily didn't put a notation to indicate that we're just looking at that state. That's why the derivative is at 0. So thank you for those corrections. So the second part then. So the title was Quantum Information in Quantum Thermal Machines, but so far there's no quantum information, only thermal machines. So now we're going to start talking about quantum information. And I ran into the sort of tricky situation that this is primarily a thermodynamics audience, but probably some of you know quite a bit of quantum info and some of you probably much less. So I'm going to put the bar from the beginning and try to put out some basic notions of quantum information. And to the share of you that already know these things, I apologize in advance, but I want to get everyone on board. The key question that we now want to use to put quantum information into this context is to say, what is so quantum about all these quantum thermal machines? A naive answer is, of course, obvious.
Thank you.
I feel I'm sinning, no? Right. So what's so quantum about this machine? The naive answer is, of course, that, well, the system is small and microscopic, and we believe small microscopic is quantum, so we use quantum formalism, and that makes it quantum. But to some, hopefully many of you, that should not really be a satisfactory answer. What's so quantum about, using bras and cats just for a small system? The better question is, can these machines do something that are somehow genuinely quantum, somehow non-classical? Can they perform a task that a classical system couldn't do with the resources made available? And if you want to ask questions about non-classicality, then you have to venture into the realm of quantum information, where these things are studied really broadly, both in terms of foundational matters and applied matters. So here we'll just scratch a little bit on the surface of notions of non-classicality, centered about the message that there is a whole fauna of them. And some are stronger than others, some are just completely different from others, but many of them tell you something about what is so genuine in a quantum process. So we'll talk first about entanglement as a sort of most popular notion, and then about teleportation as a more sophisticated notion of non-classicality. And once we have done that, I will try to construct yet another quantum thermal machine, with a completely different purpose than the ones that we have seen so far, and try to see if we can spot some signatures of true quantum behavior. So with that said, I'll have to go back to entanglement from scratch. So recall briefly, for those of you who know, and for the first time for those of you who don't know, that a system that is composed, a pure state, that is composed of, say, 2 qubits, is called a product state if you can split it into something that happens on the 2 Hilbert spaces separately. So this happens on system A and this one on system B. If you can factor it, it's called product state. Here, it's very easy to tell whether something is entangled or not. Entanglement just means it's not a product state, so it's a negative definition. Anything that isn't this form is entangled. So what can you do? You can drop one of your systems and safely say that if I drop one system, the other system has to be pure, because by definition, it's independent of the other. And pure states have 0 entropy, so all product states have 0 entropy. If it's entangled, some information must be lost because it's not a product state, so you have some entropy. And that gives you a necessary and sufficient condition for entanglement detection. Then, of course, you say, well, there is a whole field called entanglement detection. Why does that exist if it was that trivial to detect entanglement? And the answer is, of course, that pure states are easy and mixed states are not. So the notion of entanglement is much richer if you take it to the regime in which you don't have pure states anymore. And in fact, that's a good general rule that you should always consider your states to be mixed. So a mixed state is called separable, which is the analogy of not being entangled, but for mixed states. The idea is then that you can write your system as a convex combination of these product states. So you can view it or think about it as something that happens in the lab. That in one lab you do something, in the other lab you do something else, and you can pick up a telephone and coordinate what you do. Local operations and classical communications. This is in fact a free resource in the resource theory of entanglement, which you can then think about in the picture that Matteo already taught everyone on Monday. So locally in one laboratory, you create one state, and in the other laboratory, you create another state, like that. And then you mix them over your telephone or whatever medium you have with some probability. So this becomes a convex combination. You can pick any states you want and any probability you want. The way to think about it geometrically, so maybe let me add, this is separable. The simple geometric picture to have in mind is that the set of separable states is this convex region. It's convex because you can always take the convex hull of anything here. So any point that wouldn't sit inside here can just be modeled by mixing things on the boundary. And the things that sit on the boundary are, of course, these product states. So inside here, you are separable, and on the boundary, you have the product states. So entanglement now in the mixed regime means that you cannot find a separable decomposition for your state. There exists no probability distribution here and no choices of local state that can reproduce your density matrix. And now you could ask, how do I know if a state has this separable decomposition? And the answer is that you typically won't. It's an extremely hard problem. But only in some very simple special cases can you give a fully satisfying necessary and sufficient condition for entanglement detection. And for our thermal machines that we will be looking at, you saw one with a single qubit, another one with 3 qubits. We're going to look at small cases. So the simplest one we will focus on is just the one of 2 qubits, where you have a very simple entanglement condition, which is both necessary and sufficient. This is called the positive partial transpose criteria, or PPT for simplicity. It was formulated in the 90s already. It is one of 2 exceptional cases in which you actually can characterize entanglement completely. The idea is extremely simple. It is the principle here states that if rho is a 2-qubit state, let me write it like that, sub 2-qubit state, then it is entangled if and only if the positive or the transpose taken over one system, here I took system A, but it doesn't matter which one I take, just take A for convenience, has a negative eigenvalue. So to see, I will show you there are reasons for one way of the theorem. The other one is complicated, and I will just leave you to believe me on it. And it's that if you have a separable state, then the eigenvalues of your partial transpose have to be positive, so they have to satisfy it. The way to see it is to look at the definition of your product state here, or separable state. If you had a partial transpose on system A, you could evaluate it immediately because you have a convex combination of product states. So the partial transpose on system AB would now act as follows. Huh? You still have your probabilities, but now system A gets a transpose. So you have and the transpose, and then nothing happens on your other system. But of course, the transpose of a quantum state is just another quantum state. So this whole thing is a quantum state. And quantum states have positive eigenvalues. So that's the end of the business. There is no negative eigenvalue. But this doesn't have to be true for entangled states, and for qubits, it's necessarily not true. So let's evaluate it properly for the type of system that we will then see that our machine is going to be spitting out. All right, I should stay on this one. Okay, so imagine that we have a particularly simple case of a density matrix. It's something of 2 qubits, so it has a diagonal row 1, 2, 3, and 4, which is normalized. And then it has a single off-diagonal component. Maybe you recall that this looks a little bit like the state we qualitatively got from the 3-qubit fridge. And the reason is that we're going to get something qualitatively like this again from our next verbal machine. So everywhere else, we just have a bunch of zeros. When is this state entangled and when is it separable? Is the question. Well, we take the partial transpose. So take a transpose on system A. Diagonal doesn't change because the transpose just gives you back itself. But these coherences are going to move. This coherence, no, it sits at the position where row number 0, 1 meets column number 1, 0. So if you take a partial transpose, you have to swap these two, which means that you now sit at row number 1, 1 and column number 0, 0. So this one is walking down there, and this one is going up there. So your state now is row 1, row 2, row 3, and row 4. And then your coherences are sitting in the corners, and the rest is 0. So this is not a state anymore if you have an entangled state. So you should check the eigenvalues. You can quickly see that 2 of the eigenvalues are necessarily 0, because in this subspace in the middle, there is no coherence. So you have eigenstates 0, 1, and 1, 0, which will necessarily have positive eigenvalues. So that leaves you 2 eigenvalues, and only one of them could in principle be negative, but doesn't have to. All of you know how to compute the eigenvalues of the matrix, so I'm not going to do it for you. Instead, I just tell you that that single eigenvalue that could potentially be negative will look like this. So you get, let's see, row 1 plus row 4, and then minus the square of their difference, plus 4 times the magnitude of the coherence squared. And what we want is for this thing to be 0 to characterize entanglement. So if it's going to be smaller than 0, we can just forget about this factor. And then we could just move one thing to the other side and say that this condition, that lambda is smaller than 0, is equivalent to row 1 plus row 4 squared, being it has to be smaller than row 1 minus row 4 squared plus 4 coherences squared. Okay, so from here you're going to get a square from number 1, 1 from number 4, which is going to cancel the squares you get from here. So you're left with the cross terms. The cross term here is 2 row 1 row 4. Here it is minus 2 row 1 row 4, and this one is going to stay. So this one you just take to the other side, call it a 4, and that 4 cancels that one, and you arrive at the closed form of your entanglement condition. So the condition for entanglement in a 2-qubit system, maybe I put the PPT here to remind you where it comes from, is that your coherence squared is larger than the product of your diagonals on row 1 and row 4. So this is necessary and sufficient. That takes every entangled state of this form. Very simple one. So by the token of viewing entanglement as an inherent property of quantum theory, something that to some extent lacks a classical analog, you have to satisfy that. But then the question from a quantum information point of view, which makes it a bit more exciting, is to ask, are all entangled states really useful for performing completely non-classical tasks? Are they all resources for quantum information? To answer this, you will encounter the whole fauna of different notions of non-classicality. And you will see that entanglement is necessary to perform non-classical tasks, but many times it's not sufficient. Entanglement has many different forms of increasing strength. And therefore, you can make a whole ladder of different notions of non-classicality and try to pick your sort of gold standard. Entanglement is rather base. To illustrate this for you, how entanglement can actually be useless in a practical and rather paradigmatic quantum information task, I am going to briefly overview some of the key results on quantum teleportation, which I believe Matteo briefly introduced in his lecture, but here we will take it a little bit further. So teleportation is probably one of those really famous protocols that everyone has heard of to some extent. And if you've taken a quantum information class, you've probably seen it in its completely idealized form. But the full story is a lot richer and I dare say a lot more elegant as well. The story of teleportation is that you have this state psi, call it a qubit for now, that you want to teleport from one party to another. But you want to do it without using a quantum channel. So you're only allowed to send classical information and share some entanglement. So the picture becomes something like this. You have your source that is emitting one qubit to each side, and it sits in the entangled state row. So you have one particle to the laboratory that you want to teleport to, and one particle in the row. In your laboratory, you can perform a measurement on this system. The common wisdom of teleportation is that this measurement should be a projection onto the 4 maximally entangled states, which look like this. I could also comment on that when I say that these are maximally entangled states, it's again, you can all again think of it in terms of resource theories. That entanglement is your resource, your local operations and classical communication, they are your free operations. And then there is a unique notion of a most entangled state, the state from which you can convert to any other entangled state by your free operations, and those are these 4 up to changes of basis. They are all equivalent of the local unit pairs. So you make a measurement in this basis, and therefore you will have 4 possible outcomes because you have 4 possible states in your basis. Those outcomes we can call 1, 2, 3, 4. And you were allowed a classical communication channel. So this one can go to the lab here and inform the recipient. You will perform some correcting unitary, depending on the communication you receive, and you will left with a state that we can call sigma. And of course, your hope is that this sigma that you created via shared entanglement in classical communication is precisely the state that you wanted to teleport. But it's rather unclear whether that is true or not. So the typical thing that you encounter when you hear the story of teleportation is that if this state here is maximally entangled, so it's one of these 4 maximally entangled states, then you can do perfect teleportation with this protocol. Sigma will be precisely equal to psi. But the thing that you typically don't see in a standard quantum information class is the question of what happens if that state isn't maximally entangled. What if I give you some state here that is not maximally entangled, but still entangled to some degree? What happens to your teleportation? Obviously, you will no longer be able to do it flawlessly because you don't have maximal entanglement. But how well can you do it? address this is, of course, based on defining a notion of closeness between the state that you wanted to teleport and the state that you ended up teleporting. And the most popular one is known as the fidelity of teleportation. And it's defined in an extremely intuitive manner. It's an average taken over all states, uniformly with a Haar measure over the state space. And for each state, you ask, how well could I teleport it? So you take the inner product between the state that you hope to teleport and the state that you ended up teleporting, which is just the probability of being projected into that one, and you average it out. This is the fidelity of teleportation. So you could then say, well, how good will this fidelity be if I'm given that arbitrary entangled state? If my state is maximally entangled, every time I will have perfect teleportation. This thing will be 1, integral averages out, you get a perfect fidelity. And more importantly, how well could you do this classically? By sharing a separable state here and then sending classical communication. How can we know if you have a truly quantum teleportation? So the answer to this was brought forward in a rather beautiful paper written by the Horodetskis, the whole family. I believe it is tensor 4. But it could be 3 as well. I'm not sure. For those of you who don't know this is a well-versed family in quantum information with a lot of very nice results. This one is from 1999, I believe. And they give a complete solution to this problem. So they tell you precisely what is that fidelity of teleportation for any given entangled state. The answer turns out to be in terms of a more fundamental quantity, which is known as the singlet fraction. So what the Horodetskis show is that the teleportation fidelity of an arbitrary state, here taken to be a qubit, is just 1 + 2 times this more fundamental quantity, I call capital F here, the singlet fraction. So this here, the singlet fraction. The singlet fraction is precisely what it sounds like. It asks you rather intuitively, how much singlet, how much maximally entangled state do you have in the state that you're using for your teleportation? Of course, if you only have maximally entangled state, you do it perfectly. And the less you have, the worse you do. And the definition of it is entirely analogous to this sort of hand-wavy intuition. It says, pick your favorite maximally entangled state. My favorite is psi plus. One of these. It doesn't matter which one you take for the definition. And then you take your state, rho, and you say you can do some arbitrary local unitary on it to try to twist it into the same basis as your favorite maximally entangled state to try to maximize their overlap. So you have some unitary acting locally on this thing. That. You may wonder why there is only a unitary here and not on the other lab as well. The reason is that if you have a maximally entangled state here, you can always do any action on it as a local one. So you could put one here, but it wouldn't generalize your definition. You can reduce it to this. That's just a technical point, but it's not arbitrary. And then, of course, you want to maximize this by twisting your rotation frame. So you have to maximize this over the best unitary that you can find. And that is the singlet fraction. So now we can think about teleportation solely in terms of the singlet fraction. And then the question becomes, what is the largest singlet fraction compatible with a separable state? Okay, so, well, we take the one that we chose here, psi plus. Recall again, psi plus is just the square root of 0, 1 plus 1, 0.
Sorry.
Yes.
Just a small question. So we don't quite know, like, if we replace the maximization to this, every local channel, will this change the value, or actually they are the same?
It will. So there are many different forms of teleportation these days. This is the most elementary and perhaps most well-known one, but there are many different protocols. This is often called standard fidelity-based teleportation. So you could, in principle, generalize this, as you say, by maximizing over a channel. And naively, you might think, well, if I let my system interact with the local environment, surely that can't boost my teleportation. But one of the very nice and counterintuitive results in this field was that actually local noise in form of a channel can actually boost your teleportation power. So you can actually activate these things. But this is more complicated than the type of teleportation that I will go into here.
The fidelity, can you repeat what the integral goes over?
It goes over the set of all pure states.
And so how does it depend on the state that you want to teleport?
So this is the average one. So you say, I give you a state that you want to teleport, and you can calculate its fidelity. And then you average that over all possible states that you could wish to teleport. And you ask about the average ability of teleporting using the resource that you were given. So there is not just one state anymore.
But it should, okay.
You have one resource used for all possible states, and you average how well you did it. Yeah. All right. No more questions, and I move on. Okay, so we wanted to see now in terms of the singlet fraction, what is the classical limit on teleportation? So to that end, we know that we must maximize the overlap between the singlet or the maximally entangled state and some arbitrary product state that look like this. So this will be our singlet fraction. So this maximization goes over these local laboratories. I have restricted to product states instead of separable ones that you might object to should be more general. But the reason that you can do this is because the separable ones are convex combinations of product ones, and this is a convex quantity. So the best one will always happen somewhere on this boundary. So without loss of generality, you can just stick to this. Now, if you just stare at it for a moment, the answer is rather obvious. The best choice you can make here is to just choose, for example, phi1 to be 0 and phi2 to be 1. And it will give you the overlap of 1/2. You can prove this if you want, but for here, you can try to convince yourselves. There is no better choice than this. So what you have is that a singlet fraction of your state that is no larger than 1/2, this is compatible with separability. So rather, okay, maybe I should draw arrows like this instead. I say that separability implies that your singlet fraction is larger than 1/2. We already know if you have a maximally entangled state, you get a 1. So that's the signature of a quantum teleportation. But anything that achieves a better result, that is a singlet fraction larger than 1/2, will imply the presence of useful entanglement. So the question then becomes, are all forms of entanglement actual resources, or at least here, this particular form of quantum information task? The answer is no. And I will show it by an immediate counterexample, because we have already derived the condition for the positive partial transpose. So let's be practical and take a single state. I should make some space for it. This one out. So I'm going to pick this state just to achieve the counterexample. So I will pick 0 here, 3/8 here on the diagonal, and then it's a quarter left. So that, and then on the off diagonal, I will take it 1/8 and zeros everywhere else. This is a valid quantum state. It's normalized at positive eigenvalues. So let's check its entanglement. Clearly, the product of the first diagonal and the last diagonal is 0 because we picked the 0 in the corner. And the coherence term is 1/8, so clearly this is satisfied. That state is entangled. But is it useful for teleportation? To answer that, we can again look at this type of states that we were focusing on and evaluate exactly what the singlet fraction looks like. Usually, calculating a singlet fraction is actually pretty hard, but because we have this very convenient 2-qubit state, one can actually do it analytically. So to see that, let's evaluate it. So we have the singlet fraction being now the trace of the maximally entangled state. So I just write these as matrices this time, but it doesn't really matter. So we have 1, 1, 1, 1, right? This is our psi plus here, projected. And then we have the state that we chose to work with, right? Oh, I should go there. I'm not to follow me. Hello, follow me. Thank you. Right, so you only have the coherence term on the single off-diagonal element. All the rest is zero. So for that reason, we have row 1, row 2, row 3, row 4, and our C sitting there. So what is this? Well, we only care about the trace, so we just check the diagonal element. The first one is going to be 0 because the row is 0. The second one is going to give you the sum of this, and the third one is going to give you the sum of that and that. Fourth one is 0 because again the row is 0, and we have a half from there. So we have 1/2 row 2 plus C plus row 3 plus C, which is just C plus row 2 plus row 3 over 2. And to have entanglement, we insist that this is larger than 1/2. So for the state we were looking at, we had our C here being 1/8. We had our coherences here being, our diagonals here being 3/8 twice. So we have on the left-hand side 1/8 plus 3/8, the 2 cancels. And this is, of course, just 1/2, which does not satisfy the condition. So we have an entangled state that is completely useless to perform this quantum information task. What that tells you is that entanglement isn't always a resource. It's all relative to the degree of sophistication that you want to achieve in your quantum resources. What that tells you is that there is actually a whole ladder or zoo of different notions of non-classicality, some of which are much more demanding than the basic notion of entanglement. So that's the little introduction to quantum information and notions of non-classicality. It is admittedly severely underperforming in comparison to what the field has to offer, but for here it will have to do. Now we want to see what these notions of non-classicality, how they can be met in an actual quantum thermal machine. Lydia, how am I doing on time?
15 minutes. Very generous.
We want to construct what is now what we can refer to as an entanglement engine. This is a quantum thermal machine whose job is completely different from the ones we have seen so far. Typical famous quantum thermal machines, or classical ones for that matter, perform classical tasks. Tasks like heating, cooling, extracting work, ticking, or whatever. These things are classical tasks that could be performed with a quantum machine. But now our aim is to take a quantum machine that does a quantum task, that is to produce entanglement itself. And the first question is then, of course, is that even possible? And we will see that it is. This is known as then an entanglement machine, or engine, I think. Entanglement engine. And the first really convincing example, I would say, that we're going to look at here as well, was done by Brask and co-authors in as recent as 2015. This is really the simplest engine you can imagine. It only has 2 qubits. So we have 1 qubit there and 1 qubit there. We will put them on resonance, so they have the same excited energy, and we allow them to interact over an interaction Hamiltonian. Just like the reasoning for the fridge, we will take the interaction Hamiltonian to be that resonant transition, forgetting about those that are suppressed due to energy differences. So our interaction Hamiltonian here, just take it to be some strength G and this sort of flip-flop interaction. Of course, we will connect it to the bath so that the heat current can try to help us performing our task. So here we have, let's try to stay consistent with my notes, a hot one on the right and a cold one on the left. Heat will flow from the hot one into the system and here into the cold bath. And we hope to harvest this heat to create a steady state that is entangled. So just like before, we will focus on the steady state regime instead of the transient one. Once more, we could say, how do we model it? We could, of course, do a reset model again, like we did for the fridge, but just to see an option, which turns out actually to be more powerful for entanglement generation, I want to spell out the Lindblad equation here. I know that this appears in the preliminaries of this class in a rather brief manner. So I'll assume that maybe not all of you know how this looks. So I'll just try to provide some intuition and some basic conditions under which this is valid. And recall that the reset model that we have already seen is a special case of the Lindblad one. So the Lindblad model tells you again how the evolution of this system is going to go. Just like the reset, you're going to have a closed part, which is just the von Neumann equation. That's your total Hamiltonian there, commuted with your state, and that's closed. And then you have your Lindblad dissipators. And I will spell it out for this machine concretely so we can see what they all mean. So firstly, we will have a rate at which your system interacts with the bath. This rate I call gamma plus. The rate at which you receive an excitation from bath number K to system number K. When that happens, you jump in energy from the ground to the excited one. That operator that represents this jump is L. They often call it the Lindblad jump operator. Another specific form of the Lindblad equation is the result that I'm not going to derive because we'll take the whole lecture, but it's the necessary result to preserve the trace and the form of the state. That is that you have positive eigenvalues. So that looks like this, which is the famous Lindblad result. Here, these curly brackets are the anti-commutators, and I'm hoping I get the daggers right. So there is a risk that this is not quite correct. So you have this. And now remember that we have a local master equation. So we are imagining that the qubits effectively only see their own path. The coupling is very weak. So we will take this limit, and therefore we will sum over this K. So each buff interacts separately, the hot one and the cold one. This tells you how you receive excitations from the buff. Of course, you can also lose excitations to the buff. So you have to add one more term. Unfortunately, maybe I can squeeze it in here. So you have one more, just like the previous, you have to take the buffs separately, the cold and the hot one. But this time you lose excitations to the buff instead of receiving at some rate. And when you lose an excitation, you jump down from the excited state to the ground state, which means that your jump goes in reverse. So you have to bring out the daggers in the opposite way to the previous one. You have, again, the same thing, but all the daggers are flipped. All right, this is the Lindblad equation. Yes?
In the anti-commutators, the daggers are wrong.
So one more.
In the anti-commutators, I think the daggers are on the wrong L. Like the whole thing has to be traceless.
So wait, is the dagger sitting there?
Yes,
Okay, yeah, thank you. Yeah, so Patrick is actually the real expert on master equations here. So if you have difficult questions, you should actually ask him. So, all right, so okay, that's the Lindblad equation. At first sight, you may think, how is the reset one of these things? It's certainly not obvious. It's a detailed calculation. For now, you have to take my word that you can reformulate the reset on this form with some additional dephasing. It is the Lindblad equation where you have deliberately added some more noise. So typically you want to use this Lindblad equation because it doesn't underestimate the full scope of your machine. You had a question?
I just want to say something as a remark. You assume that G is small enough compared to the decay, right? So that you can use the local approach, yes. I wanted to say that this is not enough because we have some examples also in quantum batteries that even with this condition, we will see some contradiction. So I just want to say that
so this is
small enough is not enough.
Well, this is a limiting case, right? It's really only valid when this is extremely weak. So it's trying to capture the effective behavior of the system. It's not precise. But moreover, that's actually not enough, right? You also need weak couplings between the system and the buff and a number of assumptions, which is good that you mentioned because I wanted to list this just so you are aware when this equation can actually be used. So some of the key assumptions that you need to arrive at this result is that you initiate in a product state. We initiate in a product state. It means your environment, the buffs, and your 2 qubits at time 0 are separate systems. This is the really low assumption. But then you need some heavier ones. The first one is the Born, the Born approximation, maybe. This assumption says that the buff is a lot larger than the system and the coupling is weak, meaning that the way you interact with the buff essentially leaves it undisturbed. You don't influence it, it's the buff that is influencing the system. This is, of course, once again, a limiting example, but it's really necessary to arrive at a simple closed master equation like this. So this is, of course, you can make it realistic in your actual system, but one should be aware of it. The third assumption that I want to highlight is the Markov one, which is again essential. And that assumption tells you that your buffs are memoryless in essence. So any correlations that you might create in your buffs, they decay really fast. Really fast meaning way faster than the time scale that actually influences your system. So this way you neglect it and say that the change in your state depends only on the state that you have right now. And indeed, that was the sort of hand-wavy heuristic that went into the reset model. The derivative of rho depended only on rho at this very moment, not in its past. And the reason is that it is a Lindblad equation, and Lindblad equations need Markov assumptions. So that's where all this is coming from. Let me then point out, let's say one word about these rates. So the rate at which you receive excitations from your buff and the rate at which you lose them. These ones have to, in the end, come from a microscopic description of your buff statistics. So they can be different things. So here I just want to give an example where you can arrive at a concrete result. So for sake of argument, let's say that our buffs are fermionic. So they're governed by the Fermi-Dirac statistic. So the Fermi-Dirac statistic, which you may all recognize, looks like this. Like that. We can also, it's also instructive to draw this thing for the conclusions we soon want to make. So I put the energy temperature ratio there and the occupation number there. So as you increase, you will arrive, as you increase your temperature, you will arrive, oh wait, maybe, okay, let's just fix the energy to 1 maybe and put the temperature there. So then here is a half. This is the case where your populations are precisely equally matched in the excited and ground state, which requires an infinitely hot temperature. But then let's also draw the negative aspect of this. So what does this look like when you have a negative one? So then you can actually go all the way up like that to number 1, which means that now suddenly all your population is sitting in the excited state and nothing in the ground state. This is a population inversion. It is what happens in a laser, and it's in fact what we had in our 3-level maser if we had chosen to run it as an engine instead. It's precisely the mode in which we produce laser light, the stimulated emission. This to keep in mind. So we have our master equation. Here we have chosen to have Lindblad, we've chosen to have fermionic buffs, which will then determine these rates. But, I will not go into them in detail here. They are in the notes, spelled out properly. So that allows us to solve the Lindblad equation in the steady state. So we again have this field. It's true we just have 2 qubits now, but I'm still not going to spell out the full solution. That will be in the notes. It's not particularly instructive to do so, but because our interaction Hamiltonian only can create coherence in that single resonant subspace, we again, just like in the fridge, have some diagonal and a single coherence term. All the rest here have to be 0 terms because of this reason. So we will have a steady state. It will have the form, which is exactly the one we were looking at for entanglement and teleportation. All these coefficients will depend on everything pretty much, no? The temperatures, the energy, the interaction Hamiltonian, the coupling at which you lose and receive, and so on. So you can then ask, can I fine tune all these physical parameters such that this thing actually is entangled? Can the machine produce entanglement just by harnessing this heat flow? A hint at how you can find it is that the main intuition for these machines is that your heat is flowing from your hot system through hot bath through your system and into the cold one. So the more heat flows, maybe that could be helpful. So the reasonable place to look for this effect is when the hot system is extremely hot and the cold system is extremely cold. This intuition works very well for fermions because of this picture. When you have a fully cold state, everything is in the ground state, and when you're very hot, you have a uniform population. Actually, this intuition was actually proven to be correct by Shishir, who probably sits somewhere in the audience, or maybe not, but he proved it nevertheless, that this heat current can tell you whether you have entanglement in your system or not. So measuring it serves as a witness of entanglement. So indeed, it was proven in this original work by Brask and co-authors that there exists a choice of temperature and everything that gives you an entangled steady state. Unfortunately, that's the upside. The downside is that this entanglement is weak and fragile and pretty much useless. When I say weak and fragile, it's a rather hand-wavy claim. The reason it's a hand-wavy claim goes back to Matteo's lecture, and it's that when you have a resource, entanglement, you don't necessarily have a global order. So you can find monotones for entanglement that tell you that this state is more entangled than this one. And you can find another monotone that tells you the exact opposite. What does it mean for entanglement, something to be more entangled than something else? It's only well defined when your state is either separable or maximally entangled, which is that unique point of the resource theory. So what you mean here is that you cannot use it for an actual to produce a non-classical effect in an actually useful quantum information task. And an example of that is, of course, teleportation. No matter how you choose the physical parameters, you will never find entanglement that is powerful enough to be useful for teleportation, that is to satisfy one of those constraints. So you can then say, well, this is somehow the minimal machine that I'm looking at. I'm not supplying it with any sophisticated resources. It's classical baths flowing with heat flowing through a quantum system. Could I supply it with some additional resource, maybe a moderate one, that I could use to boost my entanglement to the extent that it becomes useful for this more sophisticated certificate of non-classicality? The answer is yes, and the reason I have drawn this plot is precisely that. The notion of population inversion corresponds pretty much to a negative temperature. It means that your hot bath is now not only very hot, it has a population inversion, which means that it's even more hot in this picture. To achieve that, of course, you have gone out of the classical regime because you need to have a laser-like operation in the bath. It's realistic, but of course, it's not a minimal setting anymore. You supply it with some power in hope that it can give you even more entanglement back. So in this, following the intuition that Shishir proved, that the larger the temperature gradient in these systems, the better entanglement you should be able to have. The new limit that we want to look at is no longer the hot one, but rather when you are extremely close to being cold, because that is when your population is maximally inverted. So approaching zero is the analogous of being as hot as possible in these baths. So then you can once again go back to your Lindblad equation. It's mathematically a very straightforward chant. You will only have an adaptation of these rates for your fermionic system to a new temperature that is just negative this time. You can once again solve the steady state equation, try to play with your parameters and see if you can find a useful certificate of teleportation. And it turns out that this exists. I'm not going to spell it out because it's not particularly useful. Again, the full solution is in the lecture notes, but you can find a steady state that can produce you a singlet fraction of about 65%, solidly above the classical threshold. What this tells you is that small resources that can be added to rather minimalistic quantum machines can be used to boost quantum effects into an increasingly sophisticated realm. And with that, I will highlight the sort of main open problem that this leaves, which is to say, again, how can you meaningfully compare notions of non-classicality to what happens in quantum thermal systems, not necessarily limited to quantum thermal machines, perhaps in more generality. And this is, of course, something that I'm not going to attempt to answer because I don't know. I delayed my lecture at that point. So thank you for your attention.
Thank you, Armin, for a very nice lecture. Several people said it was their favorite so far. Very good. So we have a coffee break now, and we start the problem session. If you want to join, it's of course optional outside at 4 p.m. Also on this side.